Welcome to video 2 of section 5, recurrent layers. We saw in the last video how for loops work in Theano. Now we can define a recurrent layer and recurrent neural networks. Recurrent neural networks, or RNNs, are universal computers. In theory, they can implement any sequence-to-sequence mapping. This is why there are lots of people, including me, really excited about them. In this video, we will define what is a recurrent neural network and how to implement one in Theano and Keras. The dynamics of a conventional recurrent neural network can be defined by the following equations. In other words, the null state of the network is the result of a projection of the previous hidden state plus the projection of the current input plus a bias, and all that followed by a nonlinearity, which is usually the hyperbolic tangent. Note that this state 8 is updated in a loop at every time step. At this point, you might already have an idea how to implement this, don't you? Notice the difference from the equation of a feed-forward neural network, which is represented here on the right side. We can see that the information from one layer always goes to the next one, but it never comes back. The previous equations were of a classical neural network though. There are more modern architectures, such as gated recurrent unities and the long short-term memory. The difference is, long short-term memories, or LSTMs, they have two internal states instead of just one. In this case, the hidden cell C and an exposed state H. They are implemented as follows. First, we calculate four gating values: the input, forget, and output gates, which are limited between 0 and 1 by this logistic function. We also have this update gate G, which is limited between -1 and 1 by the hyperbolic tangent. The next step is an element-wise product between the previous state of the hidden cell and the forget gate, plus an element-wise multiplication between the input gate and the update. Since these values here, f and y, are limited between 0 and 1, we can think about them as differentiable pass or not pass functions. They define, for instance, how much of the previous cell will be kept in the next state of the cell, or how much the cell should forget about its previous information. Finally, we expose a version of the cell with a value limited between -1 and 1 multiplied by the output gate, which controls how much of the information in the cell should be exposed in the next hidden state. Intuitively, the hidden cell C stores long-term memories, while the gates control how much of that information exposed for short-term operations. The GRUs, gated recurrent unities, follow a similar intuition, just like the LSTMs, but information is stored for long-term using leaky integrators. Both GRUs and LSTMs perform quite similarly, and both are better than the conventional RNN. Here in our IPython notebook, we show an example of how to write a conventional RNN in Theano. Just like in our previous Fibonacci example, here our step function implements the updated equation of a conventional RNN. Here we are doing a little optimization. Note that the projection of the input plus the bias does not need to be calculated inside the for loop. So we just calculate that inner product plus the bias outside the step function. This didn't shuffle here is used to swap axes. We usually use the first dimension of a variable in Theano as the different samples, and the second dimension as time. But in our scan loop, we want to iterate through time, right? And it can't always iterate through the first dimension, just like regular Python for loops. This is why we swap the axes here. Finally, we call scan, passing the step function as first parameters. The sequences are our input projections, w times x. Output's info is an initial hidden state, and the only known sequence in this case is this matrix U that projects the previous hidden state. This matrix is also called hidden-to-hidden matrix. We compile this function as always. Here, the inputs are the input tensor x, the initial states, the input-to-hidden projection W, the hidden-to-hidden matrix U, and the bias B. After compiling, let us create a few values to use our function. Here are some actual values for our inputs. The input x will be a tensor with dimensions batch, time, and dim. If we think of x as a video, batch would be the number of different videos, time, the duration of each one of those videos. We usually initialize the RNN hidden states with zeros. They could also be trained from data, just like any other adaptive parameter in the network. We initialize the weights with ones, just for illustration purposes, and the bias with random values. We run the cell, and then we plot the results. Play with this code. Try to develop your intuition about how it works, and try to implement LSTM and GRUs, just as an exercise. If you get stuck in that exercise, you can come to Keras to see how to do that. The recurrent neural network layers are inside Keras, layers, recurrent.py, and then here you can see how to implement a conventional RNN, an LSTM, and a GRU. In this video, we learned about recurrent neural network architectures, and we programmed a simple RNN in Python using Theano. In the next video, we will talk about the differences between convolutional and recurrent neural networks. We will also see when to use one or the other.